So I guess this is always how it starts. So I want to thank the organizers for the invitation. It's really great to see friends from all three circles. You know, one of my favorite things in the triple junction of the three circles is Seinberg-Witten theory. It came from high energy physics. It's the most useful TKFT in topology. I really wish, you know, it can be made into a real topological phase of matter, and be even better to use it to build a quantum computer. That's not actually not related to what I'm talking about. So if you think about, you know, computing, many people don't, but strongly encourage. It's a very good perspective on physics, math. I've been pondering about this question for as long as I can remember in station Q, which is, what's the computation power of physical theories? And if you think about what is a computational model, it's pretty simple. So first, what is a computing problem? That everything can be abstract to a function. So therefore, a computation model just means how do you compute a function. You give me any physical theory, you can put the input of your function as a state. You hope you will hit the answer with another state, and then you want the evolution to do the computation for you. If you do quantum mechanics, that's quantum computing. And the unitary circuit everybody talking about is just a time-dependent Hamiltonian. So you can ask, what's the other possibility, the fancy theories of a quantum field theory? I would say probably many people believe nothing new. If you add special relativity and infinite degree freedom, give you nothing in terms of computational power. So that's what I'm interested for a long time. I want to prove this. In order to do that, I'm a mathematician, I told Daniel Renard. So you have to have a definition for quantum field theory. You know, you can do other things, but I'm a mathematician. You have to have your foundation sound. I think the two largest classes of quantum field theory, which are both interesting mathematically, has mathematical definition, and are relevant to real physics, I think are topological quantum field theories and conformal field theories. So that's what I will focus on. And a large part of my career at Station Q is to show that you get nothing out of topological quantum field theory. It's the same thing as quantum computing. And people call that topological quantum computing. But I want to move on to conformal field theory. So there are many mathematical definitions of a quantum field theory. There's no shortage of that. And now it's useful for me because I want your definition to be understandable by a computer that has to be finite. Cannot give me continuum. And then if you do give me this, I want to prove this, what I said. They call quantum polynomial Church-Turing physics, which is quantum field theory has no extra computational power than quantum mechanics. So I want to go one step further from TKFT, so I will do conformal field theory. And the one I really want to do is two-dimensional conformal field theory. And I want to do something invented by Station Q called anyonic chains. So that's my finite definition of conformal field theory. So what is an anyonic chain? So this was invented by Station Q. And originally just invented as an analog of spin chains. And after I learned more physics, I think a better way to say it is a version of state operator correspondence of 2D conformal field theory. I do science as some other people in real life. Everything is transactional. So when I do something, I want a return. The return is I want to use this to prove something. So what is an anyonic chain? This is the original form. So you give me any anyon model. You pick an anyon. To be interesting, probably need non-abelian. The one I really want to focus on is the generating object in SU2 level K. the 1/2. And then you form a Hilbert space by taking a tree and then have all the admissible labeling of this fusion tree. And I will only do periodic ones. So the different periodic and open is full conformal field theory versus chiral conformal field theory. I want to do the full conformal field theory. So you should complete this to a circle, and it's better to draw this way. And then you write down Hamiltonian, and I think for the one I want to talk about, J should be negative because I want antiferromatic. So you take any pair of anion, you fuse it, and then many anions come out. I want the vacuum, the trivial anion, to have the lowest energy. So that's this Hamiltonian. If you do the SU2 level K spin half, it's beautifully written down using the so-called template generators. And I will come back to template generators. If you don't know, I don't think I want to say too much, but it's as beautiful you can get in anything. So you can ask the question, what happens when you take the chain longer and longer? And one of my former students, Shakran Zini, and I wrote a paper to, I believe, the right definition mathematically, how to get the scaling limit. And the conjecture is that this is the mathematical setup. If you take the spin half SU2 level K anion, the scaling limit will be the minimal model mk plus 2, k plus 1. And the paper I had with my former student, we did this K equals 2 mathematically. It's a little bit pathetic. It's free fermions. I want to do all the high level, but nobody can do it. I can do neither. So, but I have no doubt about it because there's a physical proof. They just do simulation and they just converge. So I really want to do K equals 3 for many years. I still cannot do it. So, but there's evidence from level 2. So one of the things, yes.
So is there some coset hidden there then? This is like GKO, no? Because to level K.
In this particular case, you don't need coset. It's a subtle question about, which one. Actually, there's a very subtle thing, like which field is a peer or something. There are lots of subtlety. But this is the cleanest.
So when you say that that's the scaling limit, what would for you be a proof of that?
I'm a mathematician. Hilbert space means nothing to me because the real thing is the chiral algebra. There are two versions. Either you show the local algebra convert to a VOA, or you do the smear field is convert to a local conformal net. We can prove both for level 2. So I think this is a subtlety. I wouldn't say people overlook, but people don't pay attention. The local algebra is the key to a quantum field theory.
So there are also many Hamiltonians that you can define on that Hilbert space. So for which Hamiltonian is your conjecture actually?
What's the?
Well, on that Hilbert space you can define many Hamiltonians.
The Hamiltonian is the one which.
The simplest one.
Yeah, the simplest one. Yeah. The reason I use the word original because there are lots of generalization. I don't call them anyonic chains. So I only do nearest neighbor fused to anyons. I pick up the ground state. I don't add another nearest neighbor. I don't add a theta to it. It's the one very original in the paper I cited. This is a total different talk if I want to give, which is what is the real definition of a scaling limit of a spin chain. So one of the things we did in the paper, the early one, is that we discovered something called topological symmetries. If I'm not mistaken, this might be the first time in lattice model we use some generalized symmetry for something useful. So what we do is we use this so-called topological symmetry as a part of the argument that the limit is a conformal field theory which is stable because symmetry excludes. exclude many perturbations. So a different way to look at the anyonic chain is the following. So give me an anion model. You always have a TKFT associated to it. And then you pick an anion. You have a Hilbert space. And that Hilbert space is nothing but you take the torus, you puncture L times, and label each puncture by the anion. And then you ask the Hilbert space for this TKFT. And that's exactly the same Hilbert space. You just write down a particular basis using the fusion tree. And then you can define a symmetry operator. Just put a string in the middle, labeled by any anion. And this TKFT can be constructed by so-called string net thing, which is just a bunch of links inside. And that gives you action on the state, and that's your operator. So it's a topological symmetry by tautology. This is all inside the same theory. They fuse any way you want it. They're all consistent. So, but you can write out using 6J symbols. So the thing about this topological symmetry is obviously if you put two, you can fuse them. It doesn't matter if you fuse them before or afterwards, they are the same. So that means they follow the fusion rule. And one magic about anion model is the whole fusion algebra is abelian. A tensor B is P tensor A. And actually, you can do even better. There's a famous S matrix to diagonalize of them. But actually, that's not the magic. The magic is that you diagonalize the fusion matrix, and the eigenvalue also come out of this diagonalizer. And that's gives Verlinde formula. So it's an abelian algebra, and just by simple math, then this topological symmetry form a representation of the fusion algebra. It's abelian, so it has to be direct sum of characters. So it's just a bunch of direct sum of the characters abstractly. And I'm interested in what's the eigenvalues. And it turns out actually you can do a little bit better based on the following fact. Every character of a anion model fusion algebra is given by a row or column of the S matrix divided by the first one. That's a non-trivial observation. And then you know that the eigenvalue has come from S matrix. Actually, it turns out you can do even better to argue that they are just this difference with certain multiplicities, which is the dimension of certain total charge. And then you jump to immediate conclusion that a topological symmetry is invertible in the sense of as a matrix if and only if there are no zeros in the corresponding row or column of the S matrix. So for example, for Ising, the M sigma would be not invertible because there's a famous zero in the middle of the S matrix. For Fibonacci, will be invertible. So, and there's actually a beautiful fact, actually. In a weakly integral anion model, which means all your quantum dimensions are square root of integers. And then, if you take any anion whose quantum dimension is a proper square root, which means it's not an integer, and that row or column has to have a zero. That's a non-trivial theorem. So why do I care about this topological symmetry beyond what we used before? So I want to use them as gate for quantum computing.
So maybe just a quick question there. So your definition of invertible symmetry?
Or as a matrix.
Is as a matrix.
Just as a matrix.
So not like there's another
not,
M.
Not your invertible symmetry or something. This is him first. So you cannot argue against it. Okay. The last I said is I want to use the new application I want to use them is for quantum computation. So that's how we'll switch gear to quantum computation. So in general, if I give you a quantum field theory, you want to say I want to do quantum computation with it. What do you mean? So actually there are two questions here. One is you want to say I can simulate the quantum field theory by a quantum computer. And the other is how do you compute with a quantum field theory? So I want to do quantum field theory not as the real physicists do. So I want to take them as Hilbert space. So you can easily formalize them into almost the same axiom as quantum mechanics with two differences. First, the Hilbert space is attached to space-time, not space. And then that almost tells you it has to be infinite. It's basically integral of all the space slices. And then you don't have a Hamiltonian evolution, you have a representation of the generalized Poincare group onto your Hilbert space. That's your evolution. Otherwise, they are the same axioms, except your Hilbert space now is space-time. If you do this, and then I can roughly say what it means by quantum computation with quantum field theory. So give me some space-time in a certain quantum field theory, or you get a Hilbert space. I want the Hilbert space to be sandwiched between qubits. And then, if you want to say I simulate anything of the quantum field theory, you just look at this square. You want whatever happens, your quantum field theory can be simulated by this qubit space. There are a lot of subtleties. Let's not, talk about those things, but that's what you mean by simulated quantum field theory. And you want to say quantum field theory contains quantum computation, you go to this square. Any quantum circuit here can be implemented by something here, the evolution for your quantum field theory. So that's what it says. And this is exactly what I did with my collaborator friends for many years for topological quantum field theory. So we did this mutual simulation. And basically, we simulate evolution of topological quantum field theory. We approximate the partition functions. And we compute using braiding. And there are lots of ingredients make it work. So I won't go them one by one, but I will basically mention them when I talk about the difficulty of conformal field theory. So now we go to the next, what I do if you want to say I do quantum computing with a conformal field theory. The evolution probably is replaced by representation of the Diffie-Hellman group or the Hilbert space. And you want to approximate correlation functions. And now you get lots of issues. First, you get a Hilbert space which is infinite dimensional. Another difficulty is the Diffie-Hellman group, as far as I know, there are no obvious generating set, like the braid group. The braid group, you can braid the two, and the mapping class will have a Dehn twist. Here, you don't have agreed upon elementary generators. And actually, the key make QKFT works is a locality not in the way people normally see, is that the QKFT Hilbert space has a gluing formula. If you want a state on a hygienic surface, all you need is to cut into pair of pans and then re-resample. And I'm not aware of such a formula for general quantum field theory, in particular conformal field theory. Actually, there's a very disturbing theorem in quantum field theory. I forgot how to pronounce something about vacuum state, or any patch will get everything. So there's some serious issue there. So if I want to do quantum computing with conformal field theory, I have to address these issues. So this is ongoing work with my student that was here, Sawyer. So to do quantum computing, you have to ask what are the qubits, what are the gates. And what we want to do is choose n qubit in an anyonic chain of certain length. And that would be my quantum computing qubit.
Just a clarifying question. Can you go back to the slide of that sandwich?
The sandwich.
Yeah. So this is, do we expect this to be true for non-topological quantum field theory as well?
Yes, that's the Turing-Church thesis.
I see, okay.
The whole point is it cannot be wrong because you have to formulate it correctly. What I'm saying is that you cannot say I'm wrong because I insist you formulate the problem to make this correct. And the whole subtlety has to do with how to control errors. And I didn't explain, but the class BQP stands for bounded error quantum polynomial time. So it's definitely, I'm not the one who really in the first one. I think many people thought about this. It's pretty much believed. There's nothing new for computer science in terms of quantum field theory other than made yourself very miserable. So, so the proposal, which is relatively preliminary, is that we want to embed it in qubit inside some states of anyonic chain. I put enough words to protect myself. I really don't know exactly yet how to choose it. So the point is that I need to choose the states in the anyonic chain which have wear correspondence in the limit conformal field theory. This is a very subtle question, and that's the word scaling means. So, but that's not the one I want to talk about today. I really want to talk about a little bit about its gates. What do you do to computing? And obviously, you have an anyonic chain, you can braid them. And the problem is the braiding are not symmetries of the anyonic Hamiltonian. And I don't regard that as a good gate if you do that. Because I want to compute using conformal field theory. The conformal field theory is the limit of the low energy states. I want to preserve the low energy states. I need the gate to be a symmetry. So although this is not a symmetry, but my whole thinking is it's just that we need to make it work. So we need to approximate this. So how do you approximate the braidings? So, I think I already said this. So basically, my proposal is braidings are not symmetry, so therefore I'm not entitled to use them as gates. What I could do is entitled to all the symmetries, and I would propose that you use unitary symmetry as a gate and use Hermitian as measurement. And if they are neither, then you're out of luck. We don't know how to use them. If you do, immediately you get too much computation power. So then the question is, do you get universality? Are those two operations will give you a universal quantum computer? I don't know. This is a Sawyer's thesis if he succeeds. So now let me back to the question about approximately braiding with symmetry. So it turns out the relation of braiding with conformal symmetry is an independently interesting question. And they go through something called the template algebra generator that I mentioned before. So the whole subject of quantum topology started with this formula here. So this is in 1984-ish. And when James discovered this incredibly new unitary representation of the braid group. And this is the representation. So you take a braid, and it's a superposition of template generator and the identity. And the template generator actually is a measurement, is a Hermitian, if you want unitary. If you look at this formula, it's pretty much like this formula you guys all know if you do quantum computing. So it says, basically, you should regard the template as the Lie algebra, regard the braiding as Lie group. And this is exactly how mathematicians define conformal field theory. So there are two well-used definitions of conformal field theory. One is invented by Borchardt, called VOA, stands for vertex operator algebra. This is pretty much a mathematical formulation of the famous Moore-Seinberg paper on conformal field theory, the chiral algebra. It's pretty much a mathematical formulation of a chiral. But these are independent. That's the beauty of science. I don't think it's inspired. And the other formulation is the local conformal net. And you should think this as the Lie group version of the definition of a conformal field theory. At this point, I'm talking about chiral conformal field theory. And then in this particular case, you can see that, as I answer Ronco's question, in the mathematical theorem, we say anyonic chain converge to conformal field theory. I prove both of them. Okay. So it turns out the most important thing is the so-called smear field. So the difference of the two, for those who care about mathematical quantum field theory, there are two standard ways to think about mathematical quantum field theory. One is just like physicists do, using an unbounded operator. It's horribly difficult, but can be done. That's basically this side. And then you can do a little bit of changing using only bounded operator. That's this side. And the way to go between them is the smear field. So basically, what you want is to use something called smeared quantum field, conformal field, and that will be my real gate for quantum computing. Unfortunately, there are no good choices at this point, which I know can be used. So then I want to do my own thing. I want to say, okay, what's the relation, the exact relation of temporally generator and conformal symmetry, which is the Virasoro generators. And it turns out actually conceptually it's very, very easy. If you just take the template generator and you pretend it can be localized at any angle of your circle, in the scaling limit, it should converge to the conformal field corresponding to the state, which is the conformal one, the stress energy tensor. So basically, the relation is that the template generator and the conformal Virasoro generator are Fourier due to each other. So they are Fourier transform of each other. And that tells you why it's a bad intuition to get the mathematical scaling limit, because when you look at the anyonic chain, that's a physical theory which is a space local. If you look at the VOA, that is described by energy local. It's totally different. That's why a complete algebra localized becomes completely spread in conformal Ln, because that's a conformal energy local thing. So that's basically what it is. But it's a beautiful question to understand exactly how those two are related. And regarding this is a really interesting incidence of how conformal symmetry, which is continuous symmetry, emerged from lattice. Exactly. Not just argue.
Is this statement special to the SU2 level K case, or do you think this is more general?
No, it should not be.
What?
It should not be. It should be a general phenomenon.
But in the more general case, I guess the conformal field theory that you will land on will have some extended chiral algebra.
Yeah.
But the temporally only
sorry. I took back my answer. If you only consider template generator, yes, only get minimal model.
I see.
But if you want to get, throw in other charges, then it's a different thing.
Okay, thank you.
Yeah. Okay, sorry. I'm saying this setup of anyonic chain is general, but for template it's only minimal model. Yeah.
So the data of anyonic chain is just a fusion category, but we could have infinitely many VOA with the same fusion category. So how you would expect that starting from an anyonic chain, in which conformal field theory you're going to land on?
Okay, so let me guessing a little bit about your question. So I don't do anyonic chain for fusion category, for the reason I strongly don't believe they convert to conformal field theory if they don't have Brady accidentally. So therefore, I don't really talk about this, fusion.
Right, but even if you pick an MTC, there could be infinitely many VOA associated with the same MTC. How do you know which VOA?
So for each anion, you will get one, but you might get different one from different anion. That's I agree. See, I have a anion model, which is MTC. I pick an object that gives me the spin chain. It's convert. In good cases, should be a conformal field. You pick a different anion, potentially you will get a different conformal field.
Okay, thanks. I'll ask you later.
Yeah, okay.
How would you get the monster VOA from that construction?
Get what?
Like the monster VOA, which only has vector as a modular vector.
Or you just take the vacuum as your spin chain.
Line.
Anyway, we can talk more. It's not something you can get everything, but let's hope for the best. Anyway, so I consider, I will finish just maybe one more slide or something. So the thing really interests me was these formulas. So this actually, I discovered with my former student Moji independently, and then later we were told they call Koo-Saleur formula. But then we discovered our formula is slightly different from their formula. Actually, it's slightly better if you want to do real numerical simulation, because our formula converge faster, but analytically they're the same. Which is, how do you take, so here what I want to do. You have a continuum theory you want to get as a limit of a lattice model. I want the story to be, everything here can be obtained exactly on the lattice. Nothing more, nothing less. Okay. So that's what I want. And for conformal filtering in 2D, the most important thing is the higher Virasoro generators. In a sense, they are unphysical. So how do you get them? And that's this formula is. You take the template generator, because I said before, it has to be non-local with respect to space, so you sum them up over the whole chain with cosine. And if you want to do the other things, and we know formally these are just derivative of the former one, and the derivative of cosine is sine, and the derivative in the algebra is the commutator. So that's give you this convergence. And as I said, I can prove from level 2, I have no doubt about the truth of this formula, but it's very difficult to prove that. So I will end with some open questions. The first one is, I believe every anyonic model is the representation category of a conformal field theory. It's basically, that's how I think about quantum Hall state. You have a discal quantum Hall state, it's just foliated by conformal circles. And we get the boundary, that's your conformal field theory. And this one I already alluded in the talk, which is, I want to choose the qubit to be the scaling state, which exactly gives you state in the conformal field theory. And that's a very subtle question. The one I'm really interested for this whole discussion is if there's possible generalization to 2+1. And of course, there's a dream here to get a 3D Ising. So I don't think it's impossible. And that's what I really hope for. Okay, I think I will stop here. Thank you for listening.
If I'm not mistaken, most of your talks concern rational conformal field theory.
Yes.
I wonder, do you have any comments on the irrational conformal?
I don't think it's really matter that much. You guys convinced me the 3D Ising has an irrational exponent. So what it is that this magic formula, I think it's due to Cardy, which is you take the spectrum on the circle, it's the eigenvalue give you the scaling dimension.
Yes.
The eigenvalue.
Yes.
So if you think about it, it's more reasonable the eigenvalue is irrational than rational.
Absolutely, yeah.
Yeah, so actually that's why I think it not really matter. What you need is, you need to take the two sphere, write down a good Hamiltonian, which give you the 3D Ising. And then you just compute the eigenvalue, that will give you the irrational.
I guess I was even asking the question in 1+1D.
I think you can do the same thing. The only difference is that you take a finite chain, and then you do the linear algebra to diagonalize into eigenstates. And there's a subtle thing about, where to truncate, called low energy. And that thing goes to infinity. So there's no problem of getting infinite many states. Because just as the chain goes up, you get an infinite field. And the only difference between 2 and 1 dimension is you should always get infinite many. But in 2D, you are cheating by using Virasoro algebra to group all of them together into finite. You use a bigger symmetry than really what it, in a sense you are allowed to use is the infinite Virasoro algebra. That makes it finite. Otherwise, it's infinite.
But maybe,
Only for rational symmetry. That's what I'm saying. It's not something, it just happened to be rational. The symmetry also extends to Virasoro, and you glue them, you organize them together. Otherwise, it would be infinite.
wouldn't the answer be you could just put not SU2, but you could put SL2C or something instead?
Sorry, I didn't get put a...
Instead of SU2 was in J, you can put SL2C.
Yeah. You can.
And then you would get probably irrational.
Probably irrational. So
things from that. I don't know.
it's obviously, that's the two different. Obviously infinite, because as your chain goes up, there are infinite many eigenstates. They should all converge to something. And the only difference is, do they organize into Virasoro thing? I mean, it may or may not be.
I had a comment about the 2+1 version of the anyonic chain. So there is this model by Inamura and Omori, which sort of takes an input fusion 2 category and then, constructs an analog of a fusion surface model.
Absolutely.
And so, but I think my question would be, what would you input there? That's the analog of your SU2.
So, actually, obviously I thought about this, because that's something I really want to do. So I think what you need is take the 3D Tori code, find the exact same symmetry defect corresponding to sigma, and you do the anyonic chain of that guy.
I got a little bit confused about is there a proposal for how to compare the input MTC to the anion chain with the MTC that governs the CFT? Because in your minimal model example, you inputted SU2 level K, and then as an output, you got the minimal model MTC. Is there any coherence between them in general? Or? No.
It's one of the most interesting questions, which is what's the connection between your input anion and the output conformal field theory. There's a paper by Andrew Gromov addressed this question. Obviously, there's a connection, but since you brought up this, I will also say there's a subtlety even for the best case. Normally, when you do numerics on anyonic chain, you don't discover all the scaling field of the limiting conformal field theory. Some of them are missing. And that's a very common numerical problem.
Yeah, I wanted to clarify to make sure I understood your point correctly. So far, you're using the CFT to build the qubits and the gates, assuming that there's no error, right?
Yeah.
So how do you envision doing error correction? Because the CFT spectrum is gapless and hybridizes with the non-scaling states, etc.
So I don't have much to say, but the reason I insist has to be the symmetry of the Hamiltonian. That's actually my error correction. So if I want to be really cheating, I just say use anything on the qubit. That's your gate. And since you mentioned the word, error correction, so what is, you do your error correction. You write out your stabilizer, and that's your Hamiltonian. What's your logical operator? That's the symmetry of the stabilizer. And that's the symmetry of the Hamiltonian. So that's my version of only compute using symmetry. That's pretty much to say you are only compute using logical operators.
So the simplest versions of these anyonic spin chains are typically integrable. Is that something that you expect that all these temporary leap spin chains will be integrable? And how does your formula for the Virasoro operators depend on the fact that it's integrable?
So I think it's a categorical fact that almost every anion model, you can discover temporary algebra in there. It's just that you take some anion, you do something, and it's a singularly generated. Anything singularly generated really would be temporally, just a different level. So in that sense, if you have more complicated one, it definitely have extra, but the temporary part is always buried in there. So there are lots of really general questions I cannot answer, but in the best case, I think that's what I focus on. Thank you.
Okay, we have time for a couple more questions if you want. Okay, then we just thank the speaker again.